In our last chapter, 34, we discussed mirrors and the concept of reflection. Here, we're going to discuss refraction, which is light that passes through a transparent material and is altered in its course by that. This process is called refraction. Our first section will be 35.1, in which we discuss the index of refraction. As light goes into glass, which is transparent, there's a block of glass. As light goes into that, it always has a speed of c, the speed in vacuum, on the outside. But when the light gets into glass or water or another transparent media, it will have a different velocity, and that velocity will be v, which is less than c. We define the index of refraction to be the ratio of the velocity of light in a vacuum, or in air, which is equivalently the same, essentially the same, divided by the velocity in the media. Therefore, it follows that since the velocity in any other media is always less than the speed of light in a vacuum, that this number is always greater than 1, because this is smaller than this. This is called the index of refraction. Index of refraction, N. Therefore, when we know N, we know the velocity of light in a given substance. And let's look at some examples of different transparent substances. If we look at diamond, it has a very, very large value of N, which means the velocity is very slow for the velocity of light in diamond, 2.419. So light is going in a vacuum almost 2.5 times as fast as it moves in a diamond. And you notice that that's larger than crown glass, which is 1.5. Benzene is 1.501. Water is 1.33. And air, you can see, is very, very close to being exactly 1, which would be that which we have for a vacuum. So to a very good approximation, you can think of this is comparable to the air is comparable to a vacuum. Now, this is why diamonds are so expensive. No index of refraction is greater than this. We get kind of close to it with a cubic zirconium, and that's why CZs, or cubic zirconia, are sometimes used as imitation diamonds very successfully. And of course, diamonds are very expensive, not only because they're very hard, but they're very clear and very brilliant in the way that they refract the light. And we'll learn more in just a minute about what that refraction means. Strong refraction index of something like lead crystal or a diamond gives this prism effect with the multiple colors, because the light that comes in is easily bent into all the different colors. As we'll see, different colors or different wavelengths are bent by different amounts and have different velocities. Now we can have something called total internal reflection, and this occurs at what is called the critical angle. I'm going to give you an example here of a triangle made out of glass. It's called a prism, and I'm going to make this 90 degrees, and therefore this is a 45, 45, 90 degree triangle. That's of course this side and this side will be equal, but this side will not. And now the reason I'm going to do that is I want light to come in on this side and go straight in and hit this side and come straight out this side, like this. In fact, when we take a prism like that and bring light in and then let it move through here, it will not continue through this. In fact, it will be bent and reflected back perfectly if we have a condition where the sine of this critical angle is equal to the index of refraction of the substance inside relative to our other substance, which of course in this case will be air. Now water has an internal reflection angle of 48.6 degrees. So water has a very strange effect. If we view beneath the water, if you were to be in water, this is air, and this is water. And if I were down here in the water, imagine a guy down here, and he's watching all this take place. Light, of course, that goes straight up will go straight out. Light, however, that goes at some angle will be bent, and it'll be bent in this direction here. Light, likewise, all rays in optics retrace. So if I took light that was from out there, it would come and go down here. Likewise, light from right here going at some other angle over here is bent drastically. And at a certain angle, it goes horizontal to the water, and that is the critical angle, and greater than that, it's reflected totally internally and does not leave the water. So you have a very interesting effect. If you had a fish down here, now I'll draw our fish, and here's the eye of a fish, and he looks out at the world, he sees light coming back along these lines. And you'll notice that the fish sees straight up, but the fish looking at a slight off angle from that central angle will see way over here. If he looks a little bit more, he sees almost over here to the shore. So if you had a fisherman over here, the fisherman appears to be right up here. That fisherman appears to be right up here. So it's very easy to spook a fish by being over there on the shore. They can easily see you in that direction. If the fish looks over to here, the light will not leave and will not enter. And if he looks further than that, the light only comes from down under the water. So when the fish looks up into the surface, into the air, he sees a circle up there, and that circle, within that circle, he sees the whole world magnified and bent into that circle, where he sees all of the external aspects of reality up there above the lake. And if he looks further away from that circle, he'll see things that are occurring down inside the lake. You'll see other fish and objects down here, and this will give us what we call total internal reflection. That's exactly like in this prism where we have internal reflection. And this angle for water, if you look at the ratio of the index of refraction of air and water, it gives us, we therefore take the ratio of the two and take the inverse sine of that, and that gives us 48.6 degrees. The reason we wanted to do this is because this becomes a 45-degree angle, and that is sufficient for ordinary glass to give us total internal reflection, exactly like the total internal reflection we have with respect to water. This is how we make a very good mirror for optics that increases the path length. If we have binoculars, there's an eyepiece here. Normally binoculars would have to be very long, but we can make them much shorter, and the light comes in, and then we use two of these prisms, one like this. The light's reflected up, then it can be reflected back around, and we use prisms, and they're a lot better than using mirrors in terms of the loss of light, and it lets us compress the size of the binoculars down considerably. So this is a very interesting effect, and for a 45-45-90 prism we do get total internal reflection. Sometimes you can actually observe that if you hold a glass like of iced tea or something like that, and you look in the side of the glass where your fingers touch, you can actually see, as the light comes up there, you'll see your fingerprint on the glass but not see outside, and due to the moisture there and the water, you will only see your fingerprint on the glass where it breaks the internal reflection and not see your finger. So this total internal reflection is used in fiber optics also, as well as prisms. And in fiber optics, we can have a fiber, and the light, usually a laser, is sent in here, And as it goes along, it's reflected from the sides of the fiber, and so the fiber can be bent around in all kinds of ways and still maintain the light and keep the light internal to it. And everyone has seen fiber optics, especially those little figures that have light that come out the hair of some little creature or something like that. It's made out of fiber optics. But fiber optics are critically important in high-speed data transmission. This all goes back to one thing, the index of refraction and what is called total internal reflection. That is, light that comes along at a certain angle or greater than that will in fact be totally reflected back within that substance. And the angle for that is given by this equation here, where the index of refraction is given by this equation here. So here are the two key equations for this section.